Next slide, Christopher, please. Hello. So here is a nice chart done by Sam Gong that summarizes the evolutionary history of the trilobites as a whole. So as I said, there are 22,000 species that are known. This time chart here exaggerates the length of the Cambrian because in the Cambrian, and even in the early part of the Cambrian, not the very base of the Cambrian, but shortly thereafter, the trilobites appear, and they are already quite diverse in form. We'll talk about the fact that early trilobites, some of them had many, many segments in their trunk region, up to and over 100 segments, whereas others that were living at the same time had in their thorax only 2 segments. So a tremendous variety in number of segments in these early groups. They were very dominant in the Cambrian and into the Ordovician, but became less so in the Silurian and into the Devonian, and then finally extended up to the end of the Permian. A rather conservative group extended all the way through the Carboniferous and into the Permian, and then went extinct at that great mass extinction, the greatest of the Phanerozoic mass extinctions at the end of the Permian. I'll point out today that the trilobites that I've shown you in the figures up to now are all later in the evolutionary history of trilobites. The ones with all those spines and eyes on stalks and the sort of crazy and ornate kinds of structures tend to belong to these groups that were the later groups in trilobite evolutionary history. Next one, Christopher. Now, of the 22,000 species, there are just a small number of species in which the soft tissues as well as the hard external skeleton is preserved. Of course, you know your fossil record here, and we've just seen Linda's beautiful shells and looked at them with the black light and seen all the patterning, color patterning that's there. Of course, there's a tremendous bias in the fossil record towards the preservation of biomineralized material. But we're very lucky in trilobites in a number of ways. And one way is that occasionally, and in a variety of different ways, the soft tissues of the trilobites are preserved. And here are 2 trilobites from the Burgess Shale, flipped on their back with their legs in the air, as it were. And you can see preserved in a carbon film here, the legs of the trilobites. This particular species is very interesting. It's the only one that has antennae at the back as well as at the front. But basically, the trilobites have antennae, and then in the head region and under the thoracic segments and the tail, the pygidium, all the segments that succeed the antennae are paired. They have a walking leg, and then they have what's called a swimming leg, the structure of which we'll look at in a moment. And what you're seeing really here are mostly the walking legs, because those are the ones that which were underneath. And they're a typical jointed leg of an arthropod that wandering on for locomotion. Now, this is a Cambrian trilobite. This is a Devonian trilobite. Their basic structure of their legs is pretty similar throughout the evolutionary history of the trilobites. And one of the questions about them is, why didn't they develop the diversity of limbs that modern arthropods have? Many modern arthropods are like a Swiss Army knife. They've got an appendage for everything. But trilobites didn't really do that. They have the antennae, and then they have these limbs, and they're a sort of integrated set of appendages, as we'll see. Because one of the things that's very new with ancient trilobites was last year, a spectacular paper was published, Christopher, that introduced, described some trilobites from Morocco that were preserved in a manner similar to Pompeii, with a pyroclastic flow from a volcano, penetrating the sea and flowing along the floor of the shallow ocean and burying the trilobites in just the manner that humans and others were buried in and preserved in Pompeii. So it's an absolutely extraordinary quality of preservation, and now with modern imaging techniques, it's been possible to look in real detail at the appendages of the trilobites, the soft tissues. So next one, Chris. So there are two species that were discovered there. I'm going to show you a number of pictures of the limbs, but here's the gut. So the mouth of the trilobite is here, not at the front. It's sort of at the back of the head, and it's facing backwards. That's also true on a horseshoe crab, but it's slightly strange that the mouth is facing backwards. The gut comes up here, and you can see the gut extending here to the anus at the end of the animal there. So fantastic to see that. There are, for those of you who are brachiopod fans, I'm going to mention brachiopods today only in that there are some free-riding brachiopods that you can see were living on the edge of the trilobite, getting a ride. Next one, please, Kristen. So I'm just going to show you now a series of these images of these two trilobites. Some of the shell was not preserved, so in this region here, we're seeing the appendages that are underneath. Next one. Here you can see a side shot, and this is almost as good as a freshly killed animal in terms of the information that's providing. You could see the antennae here, and there would be one on the other side. You can see the walking legs, but here's the swimming leg blade, and from that extending all these filaments. Next one, please. There, the filaments are super clear. Next one, please. This is another trilobite from the late Ordovician. Those were Cambrian ones. This one is preserved in pyrite, and a student and I worked on this a couple of years ago and looked in detail at those little hairs or fine spines that are attached to the swimming leg. Next one, please. And when you look at them in detail in cross-section, you can see them preserved here in pyrite. They have the shape of a kind of dumbbell. Jimbo, my former student, has argued that these are the vessels of afferent and efferent vessels that the hemocoel, the arthropod blood, would pump around, and this is where the oxygen exchange. These are where these animals were breathing in the oceans at that time. So we're getting a very good view. Next slide, please. And we're going back to the Cambrian ones now. This is the trilobite flipped on its back with its legs pointing up. This is the posterior of the trilobite. This is the head region. You can see that in this trilobite, the segments, which are, as it's upside down, here's the tips of the pleural region. And then here are the paired legs, the walking leg and the swimming leg with the gill filaments. But I put this one in to just show this ominous food groove. This is how the trilobites ate. They captured material with their spines on their legs, and then they milled it. They ground it by moving the legs. Next slide, please. We can start to see that. Here's the central food groove, and you'll see the mouth with the plate over it is here. And there are spiny projections that are, as the leg moves backwards, if you imagine my thumbs as the pivot, and my knuckles as these spines here. As my legs move back, my knuckles move forward, and that's the grinding mechanism. Next slide, please. Moving, here are the spines, just like on a horseshoe crab. The pivot is over here, these move forward, and they're sending material anteriorly to the mouth. Next slide, please. And you can see them. Those are the ones now clustered just around the mouth. So it's really difficult to imagine that we're ever going to get better quality of preservation than this. And fabulous insight into how these animals were structured and how they would have performed and fed and gone about their lives. Next slide, please. But I'm going to tell you a little bit. Most of the story is going to be things that I've had the pleasure of being involved in, and I got into the Cambrian pretty early, to be on Cambrian rocks in Wales, with my trousers falling down. I think that's a point, but there we go. Next slide, please. And I would like to just mention a few of the areas of work that we've been involved in. Because trilobites are not only spectacular for the rare preservation of soft tissues, they're also a very important group because they have a very good record of their growth series. Because they formed their shell immediately after hatching, or perhaps even before hatching from the egg, and because, like all arthropods, they went through a series of molts, in some cases, we are very lucky to get series of growth stages, what are called ontogenetic series. And through that, we can understand how these animals developed and came to be the animals that we saw in that spectacular material from Morocco. So let's think a little bit about how trilobites are structured. We've already talked about the central lobe and the lobes at the side. But if we step back a bit and think about this, how is the animal constructed? Well, the thing that jumps out, of course, is that this is an animal made of segments. There are repeated segments that are very obvious. Of course, in the thorax, the segments are super obvious because they've got a joint at each side, and they have to in order to articulate and flex as the external skeleton. The tail region at the back, the pygidium, has segments that are very obviously very clear, both in the axis and in the pleural region. But all these segments in the tail region are fused together. The pygidium is a solid plate of segments that are all sitting together. The head region, we do see segmentation. We do see evidence of a segmental construction, but it's nowhere near as clear. And it's not very clear in the lateral portions. The head region of trilobites has, though, a pretty constant number of segments, as far as we can tell, amongst all the species that we look at. They may vary in form along the anterior-posterior axis. Obviously, these furrows are differently shaped, but there's a constant number. The story with the rest of the trilobite, what we call the trunk region of the trilobite, is very different. There, the segments are basically similar in form, whether they're in the thorax or the tail, but of course they are fused together in the tail region. But trilobites are very variable in how many segments they have in the trunk region and in whether those segments are allocated to the thorax region or part of the tail plate. And the reason for that variability in the trunk region is shown in the next slide. That summarizes how trilobites grow up. So trilobites grow by molting. This is not all the series of molts that this particular species would have had. It's just a few taken out of the series to show how the animal grew. So these are the tiny, you can find in these cases where we've got the preserved growth series, find these tiny little ones and then establish the sequences, because luckily the trilobites grow in a rather clockwise way. So it's quite easy generally to connect one stage to the next stage. They don't show tremendous metamorphosis, for example. But if we look at this, and you can see the head region is here, or immediately it's obvious the eyes are here. Here's the glabella, the central region of the head, with the mouth would be under there. And although the head changes during growth, during ontogeny as it's called, basically there's no change in the number of segments in the head, totally constant. That's very different from what goes on in the trunk region. And as you can see, these tiny small ones have hardly a trunk at all. And then there's a progressive adding of segments into the trunk region. So we know, thanks to the growth series of a trilobite like this, how that process happens. And that's because this is a particularly useful trilobite to us, because we would like to know, for example, where do new segments first appear? Do they appear at the boundary between the plate, the pygidium, the plate of fused segments, and the thorax? Or do they appear somewhere else? Well, this trilobite's growth series helps us with that, because as you can see, it's sixth thoracic segment here. This is the thorax. It's got another segment behind it, and here's the tail region, the fused tail region. This one, the sixth one there, I think it is, or is it fifth? 1, 2, 3, 4, 5, 6, yeah. The sixth one has this unique spine. And we could look back into the earlier history of this animal and ask, when does that spine first appear? And here is the answer to that. Here's that spine. And you can see that it's appearing not at the front of the tail region, which is this border here. This is the animal that has 3 segments in the thorax region, and here's its pygidium. Here, 1, 2, 3, 4, 5, 6 is the 6th segment. So what happens is that going from this stage to this stage, the trilobite is adding a new segment at the back and releasing one at the front of the tail plate. So the animal literally jacks itself apart from this generative zone, producing new segments, and then those segments that are at the leading edge of the tail region are released into the thorax. Very different from any living arthropod. Think of arthropods today with a head region, a thorax, and an abdomen. And you don't take a segment from the abdomen and then change it into a thoracic segment. But trilobites did that, and it's a strange part of their growth series. And it opens up other things that we can explore. Next slide, please. So what I want to just talk about then is a few examples of interesting things we can ask about the biology of these animals in the context of these growth series. So I already mentioned that in the Cambrian, which are these 2 trilobites here, this is an emuelid trilobite, which has over 100 segments in the trunk. This is an eodiscid that has just 3 in the thorax and probably 5 more in the pygidium. So great variation in the Cambrian. Here are the post-Cambrian trilobites with magnificent features, these huge eyes, the spines, all these things. But these later trilobites generally have a much narrower range in the number of segments in the trunk region, and particularly in the thorax. So the later trilobites go in for all sorts of specializations, but with a relatively constant number of segments. So we've been interested in that for a number of reasons. Next slide, please. Partly because this gentleman, Stephen Jay Gould, who many of you may know of, a great evolutionary paleontologist, and then at Harvard, who died some years ago. But shortly before Steve Gould died, he wrote about the Cambrian radiation and argued that something fundamentally was different with developmental control. And it was possible to generate huge diversity of forms, of morphologies in a way that has since been surrendered. And now we can tweak things and fine-tune characteristics and perhaps embellish things like spines, but varying something as fundamental as numbers of segments is a thing of the past. It's a characteristic of the Cambrian. So this was sort of interesting from the point of view of, is there something unique about the Cambrian radiation that's now been lost? And I became interested in this many years ago. Next slide, please. And started to investigate this in a wonderful series of beds in the Czech Republic. And I had just a fantastic time in the early 90s working with Jiří Kříž, who was a Czech bivalve worker, and going to a location that had been studied by the great Czech paleontologist Joachim Barranda in the 1840s, and digging it out and collecting trilobite fossils. And I don't want to go into details, too much detail about the trilobites that we found, but this was a very productive lair. And there were many different species of trilobites that were occurring, and most of them were very well-behaved normal trilobites. As they grew in their early growth phase, as we just said, the trilobites add segments into the thorax. But then they get to a phase at which they continue to grow in mold, but they don't add new segments. And most trilobites are very well behaved. So they go through a phase. Here's a sort of measure of the head as a sort of standard for length. And the head isn't changing numbers of segments, so it's a good standard. And here's the number of segments. And most trilobites are very well behaved. They're adding segments as they're getting bigger, and then they get to a certain number, and then they stabilize, and they go on molting, but they don't change the number of segments. And that's true of this species that has 9 segments, and this that has 10, etc. But there's one naughty trilobite amongst this that adds segments and adds segments and adds segments, and then in these same layers, the same bedding plane collections, we can find anywhere from 18 to 22 segments, which is very unusual, and in contrast to things that were living alongside it, or seemingly at the same time, to the best resolution we can have. And I was very excited by this because this seemed to be a sort of sloppy developing trilobite of the kind that Stephen Gould had suggested might occur in the early Cambrian. And in fact, this pattern is common in the Cambrian, variation in segment numbers, whereas this pattern is common in the Silurian. But this is a Silurian locality. So it is interesting because it's an anomaly. Next slide, please. To cut a very long story of sort of half of my career short, we were able, partly through our collecting, but mostly through the collecting of Joachim Baranda's workers in the 1850s, astonishing collections in the Czech Republic. It is a wonderful locality because we do have articulated, meaning complete specimens of a whole range of developmental sizes. And what we see in this animal is the track-like addition of segments, generating new segments at the back of the tail, releasing previously formed segments into the thorax and pushing that generative zone away. And then that happens on a common trajectory for all the trilobites until they get to 18. And then we get a variety of different forms of the trilobite. And under the name box here, you would see that this one, which has 18 segments in maturity, has a longer tail region than these ones over here. That's because it has reached maturity at 18 segments. And then there's a new style of growth which switches on in the tail region when that has happened. And so because it's got to maturity earlier, it's spent longer in that second growth phase and has a larger tail. So to bring home the major point of this, when we started looking at the growth of this trilobite, it seems very variable and sloppy, but in reality, actually, there's tremendous control of the size and shape of each segment. Although we have this variation, this is a very tightly coordinated, next slide, please, Crystal, situation. And we've done a lot of work on measuring the lengths of individual segments. Next slide, please. And analyzing, if we could just go back without that picture to just the one at the top. Could you just play? Yeah, that's great. So what I'm going to show you is the most complicated graph in the whole talk. And I want to set the stage for what it's showing because it looks rather horrific. But we're going to look at the growth rates of individual segments as the trilobite grows from this stages with 9 segments up to those with 17. And what you're going to see is that the growth rate of the segments at the front region is less than the growth rate at the segments at the posterior region. And the result of that is that ultimately the longest segments are those about the 4th or 5th segment. So you'd think that the biggest segments would be the oldest segments. So the ones at the front would be the biggest because they've been around longer. But actually, next slide, or next, yeah, great. The light colors here are the segments at the front, and the progressively more red colors are the segments at the back. And what you can see is that if we look at the gradation, the slope, meaning how fast the segments are growing, what we can see is that it sort of tilts back this way, and there's a faster growth rate in the posterior segments. Next slide, please. The higher growth rates are in the back. So you can see that the growth rate is increasing. Next slide. And then we can ask the question, is this because each segment has a specific rate of growth, and the ones at the front are slow and the ones at the back are fast? Or, next slide, or next point, yeah. So that would be each segment has an individually programmed rate of growth. Next slide. Or is it more like there's a gradient of growth from slow at the front to fast at the back, and the segment grows at whatever portion of that gradient it is actually representing? So if we take the first case, please, Christopher, press. Yep, again. Sorry, go forward. Okay, let's go forward. Yeah, so that's the trunk, and this is the segment idea. So if we take the 9th segment here, if each segment has a specific growth rate, press again, Christopher, please. And again, we would expect that segment to have its specific growth rate and that be maintained. Next slide, please. Or next point. but, or in this model here, the trunk gradient, a segment in one position would have a growth rate of this amount when it's, say, the ninth segment. But next slide. In the trunk gradient model, the ninth segment is now sampling a lower portion of this curve, and so its growth rate would be less. And so we can test, does it maintain the same growth rate for that's specific to particular segments, or is it more like the control of the whole gradient of the trunk? Next slide. And the answer to that is that, if you could press it again, Christopher, thanks, is that it is the gradient model is right. The trunk gradient is the way in which growth was controlled. Next point of that. And so we are now getting insights into how this animal actually controlled its development. Dead for 429 million years, but probably a gradient of growth hormones that is constant throughout those growth stages, but having that effect. Next slide, please. Okay, so now I want to talk a little bit about some of the nice things that trilobites do and bring this then back to our friend Alacoplura that we've just been talking about. This is a carboniferous trilobite, a Pennsylvanian trilobite. And one of the famous things that trilobites do, of course, is wrap up in a ball to protect themselves. And this one is very nice because its tail fits into a nice slot in the underside of the head, making it very difficult to rotate open obstacle. It's also another specimen that we have has very nice eye facets preserved. Next slide. You can see the honeycomb lenses in this, and if you could advance the next one. These are the inside the individual lens. There are little couplets or little lens sets that are preserved within those. So it's amazing how the optics of trilobites are preserved. Very specialized function, of course, of the eye, but the general architecture of the trilobite, next slide, please, is related to its enrollment. And one of the interesting things that we looked at in the history of trilobite enrollment is that there are many styles of ways in which trilobites enroll. And the take-home message from this slide is early in trilobite evolutionary history, there are a huge range of different ways in which trilobites curled up. But later in their history, they just settled on a couple of ways of enrolling. And that is probably related to the fact that they became more efficient at enrolling and prohibiting predators from being able to shear them open. You can see this one beautifully spherically enrolled, which is a style that became very prevalent. Spikes sticking out, and its tail region here matched very comfortably against the side of the cranium, the head region, cephalon. Next slide. And here is our friend Alacoplura, because I've told you that Alacoplura varied its segment numbers, but did so in a very controlled way. And for a number of reasons I don't have time to go into, we think that this does not support Steve Gould's idea that early development, or at least when you see this kind of variability, it's a suggestion of sloppiness in development. Alacoplura is a very precisely developing trilobite, even though it shows this variation. Now let's look at what happens when Alacoplura enrolls, which we sometimes have the enrolled specimens are preserved. And I hope, Christopher, if you press this, oh yes, there it is. So here is the trilobite. Thank goodness that worked, yes. With 10 thoracic segments. So this is the stage when it is with 10 thoracic segments. Remember, this is a trilobite that has up to 22, so it's very rich in thoracic segments. And you can see that the architecture of the trilobite allows it to roll up spherically in a beautiful, compact way, which would be difficult for predators to get into. Next slide, please. Here's with 15 segments. Mr. Yep. So at 15 segments, can it do the same thing? And here's the answer. Yes, it can roll up spherically, and it can put the end of the trunk, the pygidium here, neatly against the underside of the cephalon. What about when it gets to 18 to 22 segments? Christopher, thank you. Here now, and this is all constrained by the growth gradients that we've been able to measure. The only way in which a trilobite with that number of segments can accommodate is by doing something strange with the tail. Now, this is a bit of a curious posture because you've got to push the tail right up inside an arch of the head, and there would be organs and things in there, but that is one way in which you could enroll an animal like this. Next slide, please. And there are really three options for it if it were to enroll with that number of segments. Either you could have it not effectively enrolling with a gap at the side, but that defeats the whole purpose of rolling up. Or you could do, as I showed you in that model, shoving the tail plate into the head capsule, but that seems unlikely. Or you could extend the tail beyond the head region. And I was so delighted when we came across this, because it, I think, solved one of the major problems that I'd always had with Alacopleura. And that is that, as we've said, Alacopleura is so specific about making segments a particular size and shape. But there's one thing that Alacopleura does that is extremely strange, and that is when it gets to 18 to 22 segments. And remember, of course, that segments in the thorax are released from the tail. What we find is this. Next slide, please. This is the back of the thorax and the tail region here. And these arrows are pointing to places where the release of the segment has been incomplete. So these, remember that a tail segment is released into the thorax, but it can only be a functioning thoracic segment if the suture, the joint between them, is complete. But here we've got all these incomplete. This one is released at the side, but fused in the middle. This one has two on one side that are released. On the other side, they're fused to the tail. So that can't be articulating. I think this is a good, the reason why this is occurring is because, next slide, please. Oh, let's go back to, sorry. Because this is the correct model of enrollment. If it were this, you would need your segments at the back to be super well coordinated because they've got to do a lot of bending to get into the cephalic region underneath. But if they are just sloped out like that, they're not bending. And so if there's some failure of production of that articulation, a joint that's so important in the early stages is no longer really important to the function of the animal. And so I think that was really satisfying for us after working for many years on these trilobites to have that as the result. Next slide, please. So I think in answer to the issues of this for variability in segmentation, Cambrian trilobites did experiment with numbers and form of segments, but they did so in segments that basically had a similar structure all the way down the trunk region. There's a great Greek word for that, homonymous structure. Whereas later, more evolutionary derived trilobites were very particular about the distinction between the segments of the thorax and the segments of the mature tail. You can see that this is a very different structure, and the segments very small in the axis, very wide in the pleural region. All these segments the same size, basically. Much more distinction than in the control. And so I think that's what you're seeing is what happened in many arthropods, with this trunk region becoming differentiated into a distinct thorax and pygidium. So that's the results of our investigation of segmentation. Next slide, please. I want to just finish off with a couple of things. Here's an early Cambrian trilobite from California and its pattern of enrollment. These early animals were not very good at enrolling, and if they did, even if they did, next slide, please, or next press. Yeah, this is a reconstruction, may not be plausible, but if the trilobite could enroll, it's got all these gaps that would still be open. Next slide, please. And we've been exploring this very recently with one of the oldest trilobites that's known, Schmittiellus from Estonia, and a specimen that is actually enrolled. Next slide, please. We can again do the modeling. We're working on getting a more smooth model. But as you can see, this animal would not, even if enrolling, it would not effectively shield its underside completely because the trunk is just too narrow to do that. In doing this, we also started looking, next slide, please, at the cuticle of this trilobite because it's amazingly well preserved. And in all trilobites except this one, there are two layers of cuticle. There's something called the primary layer, and then there's something called the principal layer. And the principal layer is about 3 times as thick as the primary layer. This trilobite only has the primary layer, and it's beautifully preserved in phosphate. You can see individual, that's 5 microns. So these are, 1 micron thick laminae that are preserved in calcium phosphate. Next slide, please. Here's the phosphatic layer that's being revealed. This is sandstone grains underneath. Next slide, please. And if you look down on these layers, they are like plywood. You know how plywood has the grain running at different directions at each layer. And the purpose of that is to resist cracking if the force is applied. Having the grain at different orientations on each subsequent layer makes it difficult for a crack to split and propagate in one particular direction. And that's what we're seeing on each of these individual layers. So in this earliest biomineralizing trilobite, we're seeing the absence of the sort of robust secondary layer, the principal layer. We're seeing a trilobite that doesn't enroll effectively, so it can't protect itself in that way. But already we're seeing this. Is this me? Oh gosh, I'm so sorry. I'm so hopeless at using these things that I don't even know how to turn it off. Oh God. Oh, I think that's managed to. Sorry, sorry about that. Just as I was rising for the crescendo. So you see this, beautiful cross-laminar structure, suggesting that already trilobites were becoming concerned about protecting themselves. Next slide, please. You can look down the individual fibers, and this is looking at nanoscale and see individual nitrogen molecules which indicate an organic thread work through the crystal structure. So this is primary, this is original material that's preserved. In this case, in trilobites that are about 518 million years old. This is the sort of advent of the arms race to protect themselves. Next slide, please. And here is the organic framework. When we dissolve away the crystal, you can see the original organic framework that's still preserved. I've got a long time. I want to just whiz through the last slides. Okay. Oh, okay. Next slide, please. Okay. So I want to finish with not me on the beach in Wales, but on the work that I started on this adventures and trilobites with, and then conclude with that. I started working on trilobites from the Upper Cambrian, in the mid-continent of the US. And I did that because my advisor, Derek Briggs, who's now in Yale but was in Britain at the time, had another student working in this particular setting. But it's an important one because if we think about where evolutionary novelty occurs in the marine realm, it's often in shoreline situations where there's a lot of diversity in little bays and places where populations can get isolated. And in the record of North America, the stratigraphic record, the Cambrian is one of the best times for a record in the interior. And so I started off my work, next slide please, in Wisconsin and Minnesota, following in the absolutely beautiful work done by this gentleman, David Dale Owen, the son of Robert Owen, who founded New Harmony community in Indiana in 1820s. David Dale Owen was the first federal geologist. The US Geological Survey started in New Harmony, and David Dale Owen sailed up the Mississippi and the St. Croix rivers and did this wonderful, I mean, these are the drawings he made with the strata laid out in 1852. Next slide, please. At that time, North America was tilted at 90 degrees from its present orientation, and the equator was running through it. So here we are today, somewhere here, and exposed land was this gray color. Deeper water, of course, out here, the slope, and a big carbonate platform extending over most of the shallow, drowned North American craton. And between that carbonate platform and the land was this area of sandy sediments, muddy sediments in Wisconsin. And this is called the Wisconsin Arch that is occurring there. And my trilobites that I was studying were in this region on the lateral side of the Wisconsin Arch. Next slide. We've turned this now, the Wisconsin Dome, to present day orientation. So here's the embayment. This is the land surface, ancient land surface at the time. And this is the shallow marine setting. And during the particular time that Dichelcephalus, my great friend and 50 centimeter long trilobite, although sadly always disarticulated, or almost always disarticulated, just known for the bits and pieces. In this setting, the shoreline was progressively moving outwards. It was what's called prograding. And we have a very wonderful record of a short interval of geological time being represented very well because the shoreline is moving outwards progressively, creating layers that are well preserved and sealing the trilobites within them. Next slide, please. Our colleague in Minnesota Geological Survey has done a wonderful analysis of this. This is the profile. If you take a cross section through all the beds, we don't want to go through that, but just to make the point that our understanding of the distribution of these fossils and the environments they lived in is now very good. Next slide, please. And we can do all sorts of measurements and look at the detail of the variation in these very ancient animals, even though they were distant. The resolution that we have is probably for individual beds around 50,000 years or so now. And it's amazing how in the Paleozoic we're beginning to get, in certain settings, resolutions of tens of thousands of years. So this is important for our assessing the nature of how species form, the way in which environmental controls on the distribution of the preservation of sedimentary rocks, the preservation of time. We can start to separate that or start to understand that as a context for looking at the morphological variation of the animals that are living there. Next slide, please. And I'm pleased to be working on my old friend Dichellocephalus and then some other trilobites that are occurring alongside it. This is, at the end of my career, sort of reprising things that I did at the beginning. Next slide, please. That's me in the quarries in North Britain. That's now sadly a bungalow house. It's now there, that locality in North Britain. But I want to just finish in two ways. The first way is to pay tribute to my a great friend and helper, Jerry Gunderson, who some of you might know. Next slide, please. All the opportunities that I've had to do field work and to have a career in paleontology are the result of the help that I received from Jerry and others. So I'm sorry that this overcome, but Jerry died of COVID in 2021. But like many of you, just totally interested in paleontology. If the particular rocks that were in the last quarry, if you split them with a hammer, they broke along little sandstone laminae. And the only way to collect those rocks was to collect big slabs, put them in the forest, the woods, and then when the first frost comes, it pries open the rocks and pops them open, and there are plentiful fossils in them. I would have had no idea what I was doing. I would not been able to have a career at all if it wasn't for Jerry and Ron Meyer and others who were instrumental in that. So that's the first way at which I want to finish my page review, although I wasn't quite expecting to be as overcome. But the second way I would like to conclude is that when I came to finish my PhD, I had to do a PhD defense. And I knew that I was going to be asked a load of difficult questions. And so I wrote a song about trilobites to make sure that I didn't get any difficult questions. And so this is a lament for the passing of the trilobites. Oh, look, what can this be? Swimming all over the Cambrian Sea. Is it Spriggina? No, it cannot be. Some new and strange innovation may be. Oh, come hear the tale of the trilobite stays. Niches exploited in so many ways. Where did they come from and where did they go? I've just spent 3 years and I still do not know. Paradoxides is not what it seems. More or less segments, who knows what that means? Trilobite workers in such constellation, intraspecific phenotypic variation. Oh, come hear the tale of the trilobites' days, niches exploited in so many ways. Where did they come from and where did they go? I've just spent 3 years and I still do not know. Pricklepids with their shies, the crow eyes, more or less lenses, was that really wise? Natural selection, it made the decision. Advantages reaped from peripheral vision. Oh, come, hear the tale of the trilobites' days, niches exploited in so many ways. Where did they come from and where did they go? I've just spent 3 years and I still do not know. So why did these marvelous creatures decline? Was it meteorite impacts or just too much wine? Was it drying of oceans on Pangaea's shores? Was it natural progression of one of Cope's laws? Alas, it seems there's no end to debate, to the ultimate cause which determined their fate. For trilobite workers would be out of a job. So if you discover, just keep shut your gob. That was the tale of the trilobites' days, niches exploited in so many ways. Where did they come from and where did they go? I'll spend all my life and I'll still never know. So I hope you don't have any nasty questions for me now. Yes.
Vary from each species, but from the time the egg hatch
Ah,
fully mature.
fully mature. Yes, that's something we really don't know, of course. We know about how much they grew from one increment to another, but not over the time. But if we look at a horseshoe crab, for example, so many horseshoe crabs, get to sort of 15, 20 years. The females have one more molt than the male. And in some of the texture of that variation, I didn't really have time to go into, we may be seeing sexual differences. They molt very rapidly at small sizes. So they may molt, every 2 or 3 days. When they're in their early developmental stages. And then they go on, when they get larger, the rate of molting decreases. And then they become very encrusted. So, you can sort of, yes, those brachiopods doing the things. Obviously, the brachiopods are knowing that, they're hitching a ride for a while. So we don't know, but I think on that sort of lifespan, 20 years for the biggest ones, is probably reasonable.
So a plate did not migrate with each molt.
Sorry.
You didn't think the plates migrated with each molt, one plate?
Yes. So during the phase of accumulation of segments in the thorax, it's probably the case that one segment was released each molt. Yes, that's very likely. And sometimes the time at which the last segment is released into the thorax is also the molt at which the producing new segments at the back is cut off. But in other trilobites, you can stop producing segments at the back before the last one is released, with the result that the tail gets smaller. Or you can go on adding segments in the tail plate after the thorax has been completed. So it's quite variable in that way. And in fact, modern arthropods, this production of new segments at the back, things that are called short germ band, it's quite common for post-embryonic, post-hatching acquisition and then stable numbers. But this manner of releasing these things into the thorax from the tail, that's totally unique to trilobites and weird, basically. Yeah.
Since they're similar to the horseshoe crab, And horseshoe crabs have the copper protein base
Yes.
in blood. Is there any indication that these might have the same blood? Can you
Well,
test
my friend and sort of sparring partner I was teased, Brian Pratt, who's in University of Saskatchewan, published a paper some years ago about Burgess shale fossils that are squashed and their guts come out. And he argued that Morella, which is a sort of trilobite-like but soft-bodied arthropod, had copper in those gut contents, and he interpreted that as being an indicator of that relationship. Other scientists were questioning whether that copper was introduced later. So I don't think that's been resolved, but it certainly could be the case. Yeah. Yeah.
You mentioned 1840, but when was the first trilobite identified?
So the name trilobite was given in 1771.
We teach young children, and they always want to know kind of when
the
earliest paleontologists. Say the year again.
1771, the name trilobite was given. I think it was by a German called Walch, W-A-L-C-H. And I think he interpreted them as fish, as a type of fish, but he gave that formal name. And then rather rapidly after that, in the early 1800s, there were a number of people working around Europe and North America, and many of the very common names of trilobites, Calimini and Agnostus and Paradoxides and things, were described. That sort of became very popular for people with the leisure and option to start studying this.
Which species first developed the eyes?
Well, our friend Schmidt-Ellis, which is probably not in an evolutionary sense, the most primitive trilobite, because there are quite close relatives of it that we think are more basal than primitive. But it is the oldest trilobite now, and it has eyes that are similar to most trilobite eyes, not the ones with the big fake optics with the big expanded lenses, but the small. So those were, that visual system seems to have been around for as long as they've been around, and likely evolved before the base of the trilobite fossil record. How far below that, it's difficult to say, but nothing in the Ediacaran, which you have here in Carolina, shows definitively eyes. So sometime in that interval, presumably.
Yeah, in your diagram of enrollment types through time, it seemed to show that inverted enrollment first appears in the Ordovician, then disappears in the Silurian, and then becomes a major component in the Devonian onward. Does the group that invents it go extinct and then it's evolved convergently in other groups, or is there a gap in the record of one?
That's a good question, and I can't honestly answer you that off the top of my head because I've forgotten. And Jorge Esteve drafted that diagram. I can't give you a clear answer to that, but I think what you're saying is likely the case, that it has evolved repeatedly, because there are a limited number of solutions that you can adopt if you're undergoing that posture, and so it's certainly the Carboniferous trilobite that I showed you enrolled would also have had a little gape at the end, and its antennae may have been able to stick out of that even when enrolled. Of course, that's good in some ways, but it also, of course, means that the animal could get silted up inside. So I suppose there's swings and balances. Preference. Yeah.
With the horseshoe crab, it has, I don't know, 3 or 5 eyes, but are any of its eyes multi-lens faceted?
So the two main eyes are multifaceted. And I think the light sensing sort of area in the middle of the what we call in the trilobite cephalon, the prosoma, I don't know that they're image forming, but I think there are several of them. I think there are a few, maybe 5. But I think the real sort of visual field that's being sampled by the animal is from the 2 lateral eyes. I think the other would be more like light detection if it's burrowing or something.
So there's a question from the Zoom meeting.
Oh, yes.
So Joyce said, are there any ideas about the purpose of the trident appendage or other fancy appendages? Trident appendage.
Yeah. A very difficult question, a reasonable question, but a difficult one to answer. I think Richard Fortey, who is a great trilobite worker, has advanced the idea that it was a secondary sexual characteristic, so for signaling, because it's not practical for defense, really. I mean, it's sitting right out there at the front, and it's not going to be used in predatory behavior. And so sort of suggesting sexual signaling. But, this is very sexual dimorphism is something that we would expect to occur in trilobites because it occurs widely and independently in many groups of arthropods. But it's very difficult to really build a strong case to say that it is a sexual dimorphic feature. For example, even in living arthropods, it's not the case that sexual ratios are always 50-50. They are quite often not. So you would think that obviously the range of 2 sexual dimorphs would have to have the same geological range. And you might think that you get about 50-50 of them. And, there are sort of things you could do to try and build an argument, but it's hard to really find well-supported cases. But it's likely to be there because so many arthropods do it.
Did you ever find any male trilobites that looked like they were fighting over female?
Mustard trilobites. There are, I haven't, but Steve Westrop, who was in Oklahoma and a former student of his, have found these big assemblages, 2 kinds. It's rather interesting. There are assemblages in which many trilobites of the same species have come together. And sometimes you even find ones that are similar size sort of paired up. And then you also find assemblages in which the sutures of the animals, the joints between the various components are open. And their interpretation was that these animals came together, molted, and then mated. We don't see the sexual organs preserved in any trilobite. Even those wonderful ones, of course, what's being preserved is a more tough cuticle. It's not the fine scale organic tissues. Yeah, the argument has been made that that trilobites would, like horseshoe crabs, congregate, but horseshoe crabs, when they mate, are not molting. they reach a final stage and then live long in that period, but don't go on molting. And so whilst they're mating, they retain their exoskeleton. But in trilobites, it may have been different. So there may have been these en masse gatherings and molting and sort of then mating. So quite interesting. Yes.
How would you be able to tell if it was a female trilobite or just a small trilobite of the same species?
Yes, difficult. There is there was published by Javier Hernandez in Harvard recently, and a student of his, Sarah, the name escapes me at the moment, where they found at the back of a trilobite with the appendages preserved little claspers that you may know on horseshoe crabs, the males use their pedipalps at the front to attach to the females. Well, in the trilobites, it looks like they have pedipalps at the back, and so that may be a male. In horseshoe crabs, the females are bigger than the males, at least in our horseshoe crab, our North American horseshoe crab here. And so the males have 15 molts and the females 16. Yes, one of the other criteria for recognizing sexual dimorphs is that usually in living arthropods, sexual features only become distinct at the onset of maturity. If a characteristic appears after the trilobite has its full complement of segments in the thorax, and we find two varieties, that might be a good argument. Whereas if things appear earlier, then that may not be as likely. But it's a question of sort of strength of argument, really.
Is there any theory that is more popular than the others as to why they finally just
died out? Yeah. Well, that's very interesting. So the great German paleontologist Adolf Seilacher, who did wonderful work, was convinced that the reason why trilobites, well, let me go back a step. I mentioned the Swiss Army knife analogy, and that trilobites don't show Swiss Army knife. Their appendages are, similar, except for the antennae. They're similar all the way along. And Seilacher argued that this was related to the fundamental way in which they fed. This kind of milling, moving material. They had to move as they fed because they're grinding, moving their legs. It is clear that trilobites, for some reason, did not differentiate their head appendages in the way that modern arthropods do. Insects and crustaceans do that to an extreme, but even in spiders and scorpions, there is some differentiation. From genetics, there's every reason to think that trilobites had the same toolkit of genes that modern arthropods have used to differentiate. These are the famous Hox genes, which start to differentiate one segment from another, or start the pathways that lead to making chile or maxillipod or mandibles or whatever. Trilobites almost certainly had the same set of genes, but didn't deploy them. So in this way, so Seilacher's view was that this was just essential to how trilobites fed. Richard Fortey, who we just mentioned, didn't feel that that was the case. And I think the acid test for this, and it's very unlikely to be preserved, but some trilobites didn't live on the seafloor. They were pelagic. They were swimming around in the open oceans. And it would be fascinating to know what their legs were like, because that constraint of grinding and milling when you're living on the bottom would be released in those trilobites that are floating around. And did they evolve more diversity in limbs? That would be fascinating, but we don't yet know that, and it's not going to be me who answers that question. Hopefully somebody younger.
Thank you. Wonderful.
Well, thank you. And thank you for the invitation.